Picture this. It's 11/19/4, and construction has just begun on Chartres Cathedral in France. Over the next 26 years, medieval masons will raise walls of stone that reach 120 feet into the sky, create flying buttresses that seem to defy gravity, and install rose windows weighing several tons at heights that would challenge modern construction equipment. Yet they have no cranes, no steel reinforcement, no concrete, and no power tools beyond human muscle and simple machines. The master mason directing this project carries all the architectural knowledge in his head, having learned construction secrets passed down through generations of builders who understood stone, geometry, and structural engineering in ways that allowed them to create buildings that still inspire awe 8 centuries later. How did they do it? What tricks and techniques allowed medieval masons to build structures that modern engineers study to understand their remarkable durability and innovative design? The answer lies in a sophisticated understanding of materials science, structural engineering, and construction management that medieval masons developed through centuries of trial and error, careful observation, and accumulated knowledge passed down through guild training systems. These weren't primitive builders working by intuition, but skilled engineers who understood physics, mathematics, and materials properties that allowed them to create architectural solutions that worked within the constraints of medieval technology. Medieval cathedral construction began with site preparation that required sophisticated understanding of geology, drainage, and foundation engineering that could support massive stone structures for centuries. Master masons studied soil conditions, water tables, and bedrock characteristics that determined foundation design and construction techniques. They developed drainage systems that prevented water damage and frost heaving that could destabilize entire buildings. The foundation systems used for medieval cathedrals were remarkable engineering achievements that distributed enormous structural loads across ground conditions that varied widely between different building sites. Masons understood soil mechanics and created foundation designs that used stone, rubble, and sometimes wooden piles to create stable bases for structures that would weigh thousands of tons when completed. But here's where medieval masonry becomes truly remarkable. These builders developed lifting and moving techniques that could transport and position stone blocks weighing several tons using only human power, simple machines, and ingenious mechanical systems that multiplied human strength through leverage, pulleys, and coordinated teamwork. The stone quarrying and transportation methods used for cathedral construction required sophisticated logistics that could move massive quantities of stone across considerable distances using medieval transportation technology. Masons selected quarry sites based on stone quality, accessibility, and transportation routes that could handle heavy loads using ox-drawn wagons, river barges, and sometimes specially constructed roads. Stone cutting and shaping techniques were remarkably precise, allowing medieval masons to create perfectly fitted joints that required no mortar while achieving structural strength that has lasted for centuries. Master stone carvers understood grain patterns, stress points, and cutting techniques that maximize stone strength while minimizing waste during the shaping process. The lifting systems developed for medieval construction used sophisticated combinations of pulleys, windlasses, and human-powered cranes that could raise multi-ton blocks to heights exceeding 100 feet. These mechanical systems were carefully engineered to provide maximum lifting capacity while ensuring safety for workers operating at dangerous heights with primitive safety equipment. The pulley systems used in medieval construction were remarkably sophisticated, using multiple pulley blocks to create mechanical advantage that allowed small teams of workers to lift loads that would otherwise require enormous human effort. Master builders understood the physics of mechanical advantage and designed lifting systems that optimized efficiency while maintaining safety margins. The scaffolding systems used for medieval cathedral construction were temporary wooden structures that provided access to work areas while supporting workers, materials, and equipment at various heights throughout the construction process. These scaffolding systems required careful engineering to ensure stability and safety, while providing flexibility to accommodate changing construction needs. Wooden scaffolding construction required skilled carpenters who understood structural engineering and could create temporary supports that were strong enough to handle construction loads while remaining lightweight enough for efficient assembly and disassembly. The timber used for scaffolding had to be carefully selected and properly seasoned to ensure adequate strength and durability. The mortar and binding systems used in medieval masonry were sophisticated chemical compositions that provided strong, durable bonds between stone blocks while allowing for slight movement that prevented cracking under structural stress. Medieval masons understood the properties of lime, sand, and various additives that created mortars optimized for specific applications and local climate conditions. Lime production for construction mortars required specialized knowledge about limestone selection, kiln operation, and slaking techniques that produced consistent, high-quality binding materials. The quality of mortar was critical for structural integrity, and master masons maintained strict quality control over mortar production and application throughout construction projects. The structural engineering principles used in medieval cathedral design were remarkably sophisticated, using geometric proportions, load distribution, and architectural elements like flying buttresses that transferred structural forces efficiently throughout buildings. Master masons understood structural mechanics and created designs that were both aesthetically pleasing and structurally sound. Flying buttresses represented one of the most innovative structural engineering solutions in medieval architecture, allowing builders to create tall, thin walls with large windows while maintaining structural stability through external supports that transferred load forces to massive external foundations. These systems required precise calculation and construction to function effectively. The geometric planning systems used for medieval cathedral design were based on mathematical principles that ensured proper proportions, structural stability, and aesthetic harmony throughout buildings that took decades to complete. Master masons used geometric construction techniques that could be executed with simple tools while achieving remarkable precision and consistency. Mathematical knowledge among medieval builders was more sophisticated than often assumed, including understanding of geometric principles, proportional relationships, and structural calculations that allowed them to design buildings that were both beautiful and structurally sound. This knowledge was often encoded in traditional proportional systems that could be applied using simple measuring techniques. The workforce organization for medieval cathedral construction required sophisticated project management that coordinated hundreds of skilled craftsmen working on different aspects of construction simultaneously. Master masons developed management systems that ensured quality control while maintaining construction schedules that could span multiple decades. Skilled trade coordination involved managing stone carvers, sculptors, carpenters, metalworkers, and general laborers who each contributed specialized skills to construction projects. The master mason had to understand all these trades and coordinate their work to ensure efficient progress while maintaining quality standards throughout the construction process. The apprenticeship systems that trained medieval masons created systematic education programs that preserved construction knowledge while developing skilled craftsmen who could maintain quality standards and continue building traditions. These training programs combined theoretical education with hands-on experience under master supervision. Guild systems that controlled medieval construction established quality standards, training requirements, and professional conduct regulations that protected both craftsmen and clients while maintaining the economic viability of construction trades. Guild membership provided access to construction projects, technical knowledge, and professional networks that were essential for successful masonry careers. The tool development for medieval masonry included specialized implements for cutting, shaping, lifting, and positioning stone that maximized efficiency while ensuring precision in construction work. Master masons often designed custom tools for specific projects and maintained strict standards for tool quality and maintenance. Stone cutting tools required precise metallurgy and careful maintenance to achieve the sharp, durable edges necessary for accurate stone work. Chisels, hammers, and cutting implements had to be properly hardened, tempered, and sharpened to function effectively in cutting various types of stone with different hardness characteristics. The quality control systems used in medieval construction ensured that materials and workmanship met standards necessary for structural integrity and aesthetic quality. Master masons developed inspection procedures that verified stone quality, mortar strength, and construction accuracy throughout building projects. Material testing involved evaluating stone strength, mortar adhesion, and structural stability, using empirical methods that medieval builders developed through experience and observation. These testing procedures ensured that construction materials would perform adequately under structural loads and environmental stresses. The seasonal construction planning required coordination with weather patterns, material availability, and workforce schedules that optimize construction progress while accounting for medieval limitations on winter work and material transport. Construction schedules had to accommodate seasonal variations while maintaining momentum on multi-decade projects. Winter construction limitations meant that certain types of work could only be performed during favorable weather, requiring careful planning to ensure that construction progress continued year-round through appropriate task scheduling and workshop preparation during cold months. The economic systems that funded medieval cathedral construction involved complex financial arrangements between religious institutions, municipal authorities, wealthy patrons, and community contributions that sustained construction projects for decades. Master masons had to understand these economic systems and work within budget constraints while maintaining construction quality. Material procurement systems for medieval construction required understanding of market conditions, transportation costs, and quality variations that affected project budgets and construction schedules. Master masons often negotiated directly with quarry operators, transport contractors, and material suppliers to ensure adequate supplies at reasonable costs. The technological innovations developed for medieval construction included new techniques for stone cutting, lifting, and structural engineering that advanced building capabilities while solving specific construction challenges. Many of these innovations were developed by master masons working on particularly challenging projects that required creative solutions. International knowledge exchange between medieval builders occurred through travel, collaboration, and guild networks that shared construction techniques and architectural innovations across geographical boundaries. This exchange of knowledge contributed to the development of regional architectural styles while advancing overall construction capabilities. Medieval masonry construction established precedents for modern structural engineering, project management, and construction techniques that continue to influence contemporary building practices. The emphasis on structural efficiency, material optimization, and quality craftsmanship evolved directly from medieval construction traditions. Most importantly, medieval masons demonstrated that remarkable architectural achievements can be accomplished through skilled craftsmanship, systematic organization, and innovative engineering solutions that work within technological constraints while achieving results that remain impressive by modern standards. So what tricks did medieval masons use to build cathedrals without cranes? They developed sophisticated lifting systems, structural engineering techniques, and construction management methods that multiplied human capabilities through mechanical advantage, coordinated teamwork, and accumulated technical knowledge that allowed them to create architectural marvels using only medieval technology. They proved that great architecture depends more on human skill, engineering knowledge, and systematic organization than on advanced technology, creating construction techniques that enabled them to build structures that have endured for centuries while inspiring continued admiration for their beauty and technical achievement. The next time you see modern construction equipment or visit a historic cathedral, remember the medieval mason who combined mathematical knowledge with practical skill to lift massive stones to impossible heights, creating architectural achievements that demonstrate the remarkable capabilities of human ingenuity, working within technological constraints to achieve lasting beauty and structural excellence. If you enjoy the hidden sides of medieval life, hit subscribe and give this video a like.